What I'm going to be talking about this morning is sort of the work we've done with laser and bathymetry, and it's all using Teledyne products, because the sonar is the 7125 and the laser is an Optec Ilris 3D most of the time. So the reason for doing the presentation is really geared by one of the contracts that we've just been awarded, and what I should say before moving any further on is that this presentation is, going backwards now, this presentation is really done in conjunction with the Port of London Authority, because we've done a lot of work over the years together, and it's been a good relationship, because we keep trying to come up with new ways of doing things, and we have some good clients who are quite amenable to going with no specification and trying to see what we can produce, and then liking what we produce, and then giving us more work. So it's been quite good. And also a lot of this was down to on my side of with MMT was Andrew Stanley, who's our reporting manager, but he's also our main laser guy, and he did a lot of this presentation, and also to JP Cheminade, who works with the Port of London Authority on this project that we'll show you later on in here. So the clients now are asking for well, they're starting to ask for specifications. When we started doing this, there wasn't really a specification, so now they're asking for tighter specifications, 15 centimetre 2 times standard deviations, and that repeatably over years, and you have to account for it as well. Which is kind of interesting. A very brief history on who MMT are. I had a company called Net Survey that merged with MMT in Sweden in 2011, and now we have MMT Sweden and MMT UK, and we employ about 204 people or thereabouts. And what our prime source of expertise was really high resolution mapping, because we also do side scan and sub-bottom and laser scanning underwater as well as above water. So it's high resolution mapping is what we do. So a bit of gratuitous multi-beam porn now. These are just some of the examples from some of the surveys that we've done with the 7125 in the past. We do a lot of large survey areas, a lot of hydro work for the UK government, and some coastal engineering work around there as well. And then we end up doing a lot of wreck surveys as well. And this particular wreck we've been surveying for the last, since 2008, pretty much every year, and which has been great, because it's allowed us to build on workflows, increasing the accuracy of the product, increasing the visualization of the product, and then allowing that to be used in all the different work that we do. We started doing laser with bathymetry back in, that was about 2008 is when we started looking at it. 2009 was when we really started using it a bit more, and I think we bought the first one in 2010. And this was to look at some piles around the scour, and also just to see what the laser could capture, but there wasn't really any sort of requirement for the laser. It was just to see what it could do. This one, actually, I'll just go into, because the feature pack on this one hasn't been updated, so I have to play the video instead. So this was a survey which I thought was one platform, and Jim's now telling me it's a completely different platform, but it's a platform anyway. And the reason for doing this one actually did have a reason to do when we first did it, was they were trying to work out the 100-year wave height to see if they could use this platform, reuse the platform again, because the platform had been in decommission. So this was just a spin around the platform once with the laser, and then tilt the multi-beam head at the legs, and then collect the bathy around the edge as well. And this was, I mean, the client was really happy. We worked out that, that there was, a wave height that you could actually, it was about 7 centimeters larger than what they needed, which was what they wanted to hear. And that was one of the first ones. But a lot of the time, and a lot earlier on, let me go back to the presentation here. So a lot of it was just, I mean, like that platform was just a point and shoot thing. We didn't have the software to let us see it in real time. So we were sort of hoping, you get a little view of what you're looking at, and you can easily, quickly download it afterwards when you've logged it, but you can't actually see it in real time initially, which was a bit of a pain. And it was there to, we were looking at what you can do with it, and we were looking at what the potential was of it. And it did serve a purpose in terms of the wave height, but a lot of it was just to go above the water and see what we can do and see how that adds to it. But as things go, things become more robust and are better, and the software's developing and everything else is getting there. And then we started saying, okay, well, we need to verify how the lasers performing against each other, and we need to know how the lasers performing against the multi-beam, and we need to be able to statistically analyze that data too. One of the first jobs we did with a more robust aim, and that was to try and get a 20 centimeter DTM of the rock protection. And this was the area that the laser was going to cover, and the multi-beam goes up, and we try and do it. Everyone's saying, you want to collect multi-beam laser at the same time. Well, actually, most of the time you don't, because if you have got tide, you want to use your high tide to do the multi-beam and your low tide to do the laser, and then you get your overlap. So you don't often run the both simultaneously. And here especially, you wouldn't get the overlap unless you did it that way. And then with the we took various profiles, and this is the grey is the laser, and the coloured is the multi-beam, and you can see it's tying in nicely, but it's not really. I mean, it's absolutely right for that job, but to try and put metrics on it and to try and see how accurate it was and do it, we just knew it fitted, and that was sort of good enough for that one. And then earlier on this year, it was we were a bit. More developed in how we did things, and this was for a rock armour around this is Portland Harbour, where they're swimming. They might have swam there, but it's where the sailing was in the Olympics. And we've done a number of surveys along here because there's a lot of wrecks down here. It's a great place to go to try out your multi-beam over the wrecks. And as we go through the data, we were getting a lot more. The clarity was getting there, the accuracy was getting even better, and you knew that you were onto something that is starting to become repeatable now, because we had to go down twice over different bits to do different areas, and the data was tying in together quite nicely. And also, now that we can acquire the data a bit better, we've got the patch test tools and everything. We're using Quincy here to acquire the data, and the patch test tools have been developed a little bit as well. So you know that at the end of the day that you're getting something which is good quality, but you can still improve on it. And we were trying to develop we were working to develop a project specification, and then we were given a project specification which was really quite tight, and it was really a repeatability that was wanted as well as the accuracy that was wanted. And then we're also going to use photography with the laser as well to assess the data. So I should have gone up a lot higher than that because you can't read that at all. But this is the workflow. I'll just read it because you can't see it. We're using the POS-MV, and we use POS-PAC processing, POS-MMS, to create our real-time, our post-processed position and height. The roll and pitch doesn't really, unless you screw up your offsets, the roll and pitch doesn't really give you that much extra in the post-processing, but the position and height do. And then we take that through Quincy into Fledermaus and then into the various scenes that we have. And this is an example of the POS MMS processing. This is a smart base, so it's a virtual network that we create. And then this is your typical altitude plots, and you can see there's some spikes in the data. This is going along the Thames, so this is going under bridges. The X and Y is always fine. It's the Z that you end up with a few busts in. So what that gives you, and this is just to show, this is the tide in the Thames. So we're not talking about 20 centimetre variation. This is 6 metres over the course of the survey day that we're dealing with. So it's quite dynamic. So now you've got over that much vertical range. They're looking at no more than 15 centimetre of error every year. It's quite tough. We were helped along the way here. This is a tool that Johnny B at QPS wrote, which basically takes out the spikes in the data using the true heave value to interpolate over the top, and then it writes back a new SBET that you can then load in. And this tool has been invaluable for the bridge work. It just makes life much easier. And then initially, the idea was just to go here where the coloured dots are. That's where we wanted to go to. But now they've sort of said, okay, we need to go to the top of the flood defence because they want to see how that's changing as well. And the first time we sort of did this new processing methodology was on this Rochester Bridge survey. This is just the laser part of it. There's the bathy as well for it. And the difference here was we identified some areas not just for the calibration but for a height verification. So we're looking at getting the numbers right for the height. And this was initially just for the laser. So we took a decent flat-ish area, so the top of that is kind of nice. And then we did some RTK control points over that area, and we did a 20 centimetre grid for the laser, or 10 centimetre grid for the laser. And then we just used, this is cross-check, which is a Fledermaus tool for doing normally IHO analysis. And that's a point versus surface comparison. So we took our RTK control points and took the surface that the laser did, and over those areas you got, in this case, 7 control points, and the difference here was, the mean was 2.5 centimetres, and with the 2 times standard deviation there was 13 centimetres. So that was good, but we could do better. And the real thrust of having to do this is with this Thames Tideway tunnel, otherwise known as the Thames poo pipe, and it's there's a lot of the Victorian era, 1800 era sewers under the Thames that just can't cope. Normally it's just when we're getting really high downpours of rainwater, but the system can't cope, so they're putting in a new tunnel. It's 80 metres down, it's below the Thames, and it's £6 billion, Jim? Is it somewhere around that? It's going to be one of the biggest construction projects in the world in the next few years. And what they want to do is to monitor that, they're going down in these shafts and then to do everything else underneath it, and they want to monitor the change and making sure that nothing's happening to the environment and to everyone's houses. So the idea was to produce a reference surface that we could use for both the multibeam and the laser, and the Putney boat ramp is kind of nice because you can do it on both. Then you get your Thames land surveyor, in this case JP, to go and do a lot of reference points on that surface, and then use those. And what we've actually done is use the control points to fine-tune the patch test. So they come out, you know what the answer should be, so you're backing out and for the laser it's the pitch. Like with the multibeam it's always a roll, but with the laser it's the pitch, which is the big one to try and drum out. And what we found was we started with 0.12 and we ended up going with 0.17. So the normal patch test gives you not quite within a few, tenths, but not enough. And when with this method, you fine-tune it more. And then we applied that value to previous surveys, and that meant it worked really well. So over the course of 2 years of survey, we're down to very small standard deviations comparing with each one. And then, of course, compare the multi-beam with it. So, and we've given this, you can't see it, that's a 15 centimetre is what the client requires, and this just says yes, because it passes. But basically, we're at about 4 or 5 centimetre, some of us slightly higher, and we haven't actually tweaked the multi-beam results yet. We're going to look at that as well to try and get that a bit better. But that's and these are different locations down the Thames where we've established reference surfaces. So depending on which area we're doing, we can just go over that one reference surface area. And with the laser, it's even better because the laser is more repeatable than the multi-beam because it's just that little bit more accurate. So. And then when we do the statistical analysis again, we're doing now with a lot more points over the data because we've done 199 different measurements over that ramp. And now we're going, we've increased our accuracy by a factor of 2 really. So our mean, our 2 sigma is actually now 8 centimetres and our means are still about 2. So the repeatability is much better. And then this is just a comparison between the multi-beam and the laser, which was kind of, we had to do. So that, 10 centimetres is a maximum. Everything else is normally less than 5 centimetres between the two. And then they want huge so point density. So this is both the multi-beam and the laser. Anything white is over 9 points in a half-metre bin. There's a few areas where that was more due to, this is where some of the vessels are moored, so you can't get in as much. And then this is the combined data set now. So it's, it is totally seamless, and we know, like Felix though, it looks right, it fits right, but now we know it is actually right because we've done all this correlation and comparison, and we know it's repeatable, and the methodology is good, robust, and that's that's what we want. And of course, we've got backscatter, because if you're going to be pulling loads of material out, you want to make sure that you're not putting anything back. So again, that's backscatter from the 7125. So in the conclusions for this, we started off with a point and shoot system, and now we have a fully defined, very robust, easily repeatable, and you can tell the client how accurate you actually can get, and then you can verify how accurate you can actually be. Both with the multi-beam and the laser, which was kind of the key here. We could, the two, if you're combining data sets together, then the two systems have to be as good as each other, basically, or as good as you can get. And we wanted to know it was reliable and repeatable as well, because we got the contract in the end, and that's what we have to produce. So that's me, and that's Andrew, and that's Yantlit, where the laser is on there now. And so thanks to Andrew, thanks to JP and the other guys at the Port of London, Jim included. So any questions?